In this video tutorial, I want to quickly describe how we can actually find the estimated population standard deviation when we are working with a sample. So what have we got here? We are taking a sample of measurements. These are our observations, and this would be our sample. We, for example, measure the concentration of a biomarker in milligram per cubic decimeters, which is the same as milligram per liters. And these are our observations. And now we want to know what is actually the variability, the standard deviation, not just in the sample, but in the population, in all people who have this biomarker. So from this sample, we want to estimate the standard deviation in the population. And we can also calculate the mean of the population. So we can calculate a mean of the population. And we have done that in a different video. And we said, for example, the mean would be the mean of the sample, which I abbreviate with x bar, plus minus a margin of error. And we want to do the same for the standard deviation. So eventually we want to say our standard deviation is somewhere within a certain range. So this would be the lower range and then the upper boundary of the standard deviation. And the reason why we can't write it just simply like this, like sigma plus minus a margin of error, is because it is not a symmetrical distribution. Unfortunately, we would need to work with a different distribution which is not symmetrical. And in this particular case, it would be the chi-square distribution. But this is basically as good as we would get it. The equation for calculating this lower and upper bound is a little bit of a beast. That is this equation here, but we will go through this equation when we do the calculation. Now we can already make a good estimate for the standard deviation of the population, and we have done that in a previous video. The link is in the description, and we've calculated the standard deviation, so the estimated standard deviation of the population is calculated by the equation square root of the sum of the individual observations, and I call them x sub I. These are here these observations that we have here, minus the mean of our sample, and that's this one that we've calculated here, divided by the number of counts. So we've got 8 counts here, minus 1, or in general this would be an n. So that is how we calculate the estimated standard deviation of the population. And what we need to do now is find these lower and upper bounds, and for that we actually use this monster of an equation that we have. Actually is not that bad, because what we are looking for is just simply here our number of observation minus 1, so that would be 7. That's easy. Here this s squared is actually the estimated standard deviation. So we said the population standard deviation is this estimated that we've got from the sample and which we have already calculated here in a previous video. Just as a reminder, we can do that by using the stdev.s, and that's the s, that is very important, function here, and we just simply highlight the cells that we want here to be calculated. So that would be B2 to B9, and we get this as the standard deviation, the estimated standard deviation of the population. So we've got that. So really what we need to figure out is just this value, and then we've got everything for our calculation. Now this value here is what is known as the chi-square value for the right-hand distribution for alpha half. What is alpha? Well, alpha simply is the significance level. So significance level. And or also known as the type 1 error. And we would usually set this to, say, 5%, which is the same as 0.05. So what we need to do is we need to find the chi-square value. So chi-square value for an error level of 0.025. That is this one here. And we also need to find the same chi-square value for 1 minus alpha half, and that would be 1 minus 0.05 over 2, so that would be 0.975. Now this chi-square function that I use in Excel, the chi-square.inf.rt function that we can use to calculate these values, takes two parameters. First, it takes our significance level, so that would be either alpha half or 1 minus alpha half. That's what we just calculated here. And it takes the degrees of freedom, which in this case would be n minus 1. So number of observations minus 1, so that would be 7. And now we have basically everything together. We can calculate our first chi-square value here. That's this one here with this equation. So chi-square.inf.rt, 0.025 and 7 observations, and we get a chi-square value of 16.127. We can calculate the second chi-square value, that's this one here. And again, we do exactly the same calculation, but this time we do 1 minus alpha half, and we get 1.689. And now we've got everything together, and we can put that into an equation. So for the first part here, we do the calculation square root of n minus 1 times the variance, or s squared, that is this value that we've calculated here in cell C12, divided by the value that we've just calculated here, the chi-square value. So that would be our equation. And the calculator Excel tells us that this would be 0.917. And we do the same thing for the second part of this equation here. Again, very similar to the first part, just we substitute the denominator with what we've calculated in cell C17, and we get this value here. And this actually forms the boundaries of our calculation of our standard deviation in the population. So we are 95% convinced, or we are highly convinced that the true standard deviation of the population for which we have calculated the sample is basically somewhere between, let's say, 0.92 and 2.82, just rounded. So our standard deviation is somewhere in between. So let me write this again. So 0.92 smaller or equal than the estimated population, the true population, I should say, it's no longer an estimated one, the true population, and that is smaller than 2.82. And we've calculated our previous estimate is 1.38, so it's within these boundaries. And as I said, we believe that the true population standard deviation is somewhere between 0.92 and 2.82. So I hope this makes sense. It's a lot of calculations and equations, but luckily Excel does most of the hard lifting. It would be nice to have a specific function for that, but one probably need to wait till Microsoft updates Excel. So I hope this makes sense, and thank you very much for watching.